Hello, my name is Roel Pieters and I'm with Tampere University and the Cognitive Robotics Group. And today I would like to give a presentation on robotic grasping in Agile Production. So first I want to start with some state of the art, which you can see in these videos. So on the left side, we have our traditional model-free blind grasping, as it is typically done in industry. And on the right side, you see two videos of current state of the art in deep learning for grasping. Some crucial things to notice here that, for example, on the left side in traditional based grasping, there might be vision systems. However, grasping is typically done blind. This means that the vision is not used to actually track objects, but the picking of objects is done by predefined positions on a conveyor belt, for example. Also, what you can see here is that the end effector has two grippers instead of normally one to have a more efficient system. And tasks are done typically completely with predefined motions. The contrasts can be seen on the right, where we have a deep learning-based approach, where typically a grasping model is trained with large sets of data, either in simulation or in the real world. And over time, the system learns how to do grasping with different objects. Some other differences here are that on the right side, you see a suction gripper and also a parallel gripper for picking up objects, while on the left side, it's typically only usually a parallel gripper. So from this, we can conclude that traditional grasping works well with known objects. However, there's also some limitations that we need to explain. So first of all, in all cases, there's limitations on the hardware. So even if you have a parallel gripper or a suction gripper, still this is limited to the objects that you can pick. So this has to be carefully designed and carefully decided. There's limitations on the software side as well. For example, in state-of-the-art solutions, for example, with deep learning, if you want to try the grasping of new objects, this might not necessarily be supported or even tested, which is a limitation. Then finally, there's limitations in programming, as this is a time-consuming task for all robotic systems. That might be easy for simple pick-and-place tasks, but if we go to a bit more complex handling, such as object manipulation, then it's very difficult to do. So actually, what then do we want from a grasping solution with a robot? We want this solution to be general. So with a single object, with a single gripper, we want to pick as many objects as we can without having to redesign the system. In addition, we want this to be easily and quickly trainable and executable. So we can divide this problem in a few categories, depending, of course, on your application area, what kind of sensing you used. Do you use a full 6D representation of your object, or is it a subset of that? How fast do you want to do grasping, and what kind of gripper do you use? Then another big classification difference is also whether you include a model of an object, or if you have no model, and whether this model is learned or analytically derived. So in this presentation, I want to give a few solutions for this handling of objects. And they can be seen here. So first, I want to present a compliant parallel gripper, which doesn't use any object sensing to do the grasping. Then second, a method which is based on pose estimation and the learning of a model for pose estimation. And then finally, I want to present the single demonstration grasping model, which doesn't take into account the full 6D pose of objects, but only the 2D position and orientation on a plane. The motivation from this comes from a use case that you can see here in the images. So on the left side, we have a diesel engine, which is currently being assembled manually in a factory. And the interest here is to do this robotically or with robot assistance. So the parts to handle are taken from this, which can be seen. These can be quite complex and very complex shaped, as can be seen in the middle figure. or they can be hand tools, which are typically designed for human use and not for a robot. So first, we go to the compliant parallel gripper. Just to remind, this does not include any object sensing, but gripping is typically done completely blind. So the object is placed underneath the gripper on the table, as we can see in the middle figure, and then typically a grasping action is executed. The gripper itself can be seen in detail on the right image. So this is a gripper which is completely 3D printed, so it can be tailored to any end effector of a robot. And it has different types of material. So the blue cells, for example, they are soft material, meaning that they compress under a force. If we then set the grasping force of the robot arm to, for example, 100 newtons, then this force is divided over all the cells that are in contact with an object. And in this case, since there's 20 cells, we need about 4.5 newtons to completely compress one cell. And this then looks like, as can be seen in the lower right image, where the cells are compressed to the object and they shape itself around the shape of it. So you get a quite stable grasp for handling such objects. Some videos can be seen here, where we see first small objects that are handled, bolts. So we don't define the exact position underneath the gripper, but we just assume that it will fall inside the gripper once grasping is executed. Once we go to a bit bigger objects, it also works better. Here there are some hand tools that can be grasped successfully. And also with more heavy objects, this works. So on the left side, this is about 1 kilo, a common rail diesel engine part, and a complex shaped fuel line on the right. So grasping is successful in this case. There's of course limitations here as well. We don't know exactly what the pose of objects are inside the gripper. So if we don't grasp it correctly, it might move inside the gripper. This can be seen in this video. So the object moved. So once we put it down, you actually hit the table, which is undesirable. Even worse, it can also happen, of course, that parts fall outside the gripper, since this is not sensed, which is then unsuccessful grasping. More information can be seen in this publication below, which is linked below. Then the next solution, which is deep learning based pose estimation. So we estimate an object pose and then utilize this object pose for doing robotic grasping. This is quite a popular approach, and you can find many solutions and data sets in literature, which not necessarily take robotics into account, but simply only pose estimation. But there's some limitations to this. And mainly this is on the data collection side, which is a bottleneck. Data is difficult to obtain. It's time consuming to collect data, and it's expensive. So the solution that we provide here is to rely on a CAD model and simulation to generate a data set. This can be seen in the lower figures, where we have included CAD models of the object parts in Gazebo, where you can then tune different parameters of these objects, for example, the weight, the orientation on the table in different poses, the color. Visual effects can be added, such as noise and lighting, and you can add friction to these parts as well. The next step is then to add a camera in the simulation and then use this to generate images. So on the top right, you can see these blue objects, which are Kinect cameras simulated in the world, and then each takes an image, which can be used to collect data. The data itself then looks like this. So we have on the left and middle image the color image and the depth image of the object set. And on the right side, you can see the object binary mask and the class label. This means that each individual object in the scene has an individual mask and label, which can be used to train your model. In addition, since it's a simulation, we also have the ground truth pose of each object in camera and world frame, which can be utilized. So this is all obtained from simulation. The next step is then to actually use this data set to train a pose estimation model. And then you can use a subset of the data set, for example, just RGB or depth, or you can use both. What you see in this video here is that we have tried the method PVN3D, which is linked here, to train our model and try out the model for inference on simulation again. There's different sets of parts that we've tried. So again, you see on the left this diesel engine set with different parts, then a slider crank mechanism and some planetary gearbox. In simulation, it works quite okay, but of course, this is not the same as in the real world. So some additional experiments need to verify this approach. So besides the pose estimation itself, then the next step would be to go to grasping of these parts. And this is simulated here in this video. So on the image inset on the left, you can see the correct object pose of these parts estimated, which is then utilized to grasp the object and do a follow-up manipulation step. While the grasping works successfully, the follow-up step of peg-in-hole manipulation is not successful. But we expect that this is mainly due to the simulation environment, and more experimentation needs to be done. Probably in the real world, as simulation might give a wrong solution or a wrong overview of how well the method works. So still work in progress. Then finally, I want to show this single demonstration grasping model, where instead of a 6D pose of an object, we only have a 3D pose, as we assume that we have objects lying on top of a table, and we only need the 2D position, the orientation of these objects on the table. The approach then takes a single image of an object and uses this to generate the data set and train a grasping model. We can utilize this information of only 3D, as we know where the robot is with respect to the table. Also, in addition, we know that each object can be grasped along the center line, meaning we know that we can do successful grasps. The data generation can be seen here. So as I said, we take a single image of an object and then augment this data, where we include changes in brightness, translation, rotation, and scale. And in addition, we use key points on the objects for the orientation of the objects. The data set can then be seen in the middle bottom image as an example. Here are some results in the real world, so not in simulation. On a small object set, only 8 objects and 100 trials, we received quite an okay success rate. So grasping works well for this rather simple and complex images. Complex objects. And in addition, we have integrated this in simulation as well. Again, the objects are both simple and complex, so of course more experimentation needs to be done to show that the method is robust. One thing that I didn't talk about much was actually the evaluation itself, and there can be many different methods to use. They are based on standard parts and standard task boards. One example you can see on the right here, which is the NIST task board, where you have different connectors and different parts to handle, which then evaluates grasping approaches and effectors for the task of robot grasping. Other methods simply use the object pose in 6D or a point cloud error, which is in 3D. Most importantly, however, it is the success of grasping itself. So how well can you grasp an object or an object set, and how fast can you do this, which is then important for industrial applications. One thing that these approaches do not take into account is actually the importance of the gripper, meaning that if you have a perfect pose estimate, this doesn't necessarily imply that you can do a perfect grasp as well. So this has to be taken into account. One thing that also should be evaluated is the data requirements. and how much data do you need, and how much training do you need for this data. And this is important nowadays for the data-based approaches, where the computational requirements can grow exponentially and get out of hand. I have given a few examples here in the table. So as you can see, for the compliant gripper, there is no model, there's no data, so we don't need to generate any data, meaning that we can do real-time grasping just with robot motion planning. Deep learning-based pose estimation requires a lot of data. As you can see, we needed more than 3,000 RGB and D images, and training needed to be done on a computing cluster for more than 2 hours. This meant that the model for grasping is rather large and heavy and could not run in real time. Our single demonstration grasper model is a bit lighter, so we only needed 10 minutes on a GPU for training, as we only use color images. This method produces a light model, which can run in real time on a standard GPU. Then I want to conclude with a few things to mention. So I try to explain that there's a lot of efforts ongoing in benchmarking of grasping, and several competitions exist. For example, for RoboCup or European Robotics League, and also here at IRIS, there's a grasping competition going on. But there will be another one specifically aimed for Agile production. And this is both a competition on virtual, on data, and with real robots. So for data, we consider object detection and object pose estimation, and also quality control of a fixed assembly. And this data is then used to do a real competition with robots, where a robot needs to be programmed in collaboration with a person to do grasping. The systems we consider is gear systems and the assembly of those. This is a competition that will be held once per year from now on. And if you are interested or want to compete, then I put here a link for more information. Then finally, one realization that we also made in this work is that a standard toolkit for deep learning and robotics is needed. Similar to ROS, there's many novel solutions that are provided regularly in deep learning for robotics, but they're not standardized with any toolkit. The benefits for this would be that a gap would be bridged between academic research and industrial applications, which is important. So there's an ongoing Horizon 2020 project for this called Open Deep Learning Toolkit for Robotics. And parts of the works that I presented here are being developed for this toolkit. The toolkit aims then to have a modular, open and non-proprietary toolkit for core robotic functionalities, which are enabled by deep learning. This goes from perception to cognition, so many topics are present, and also the application area of Agile production is represented. A first version of the toolkit will be released at the end of this year, where you can, as I said, where you can find the solutions that I presented in this presentation. So feel free to go to this website for more information. This was the presentation that I wanted to show you today. You can find more information on our website. And if you have any questions, then I'd be happy to answer any of these. Thank you.